Hi guys, this is Mr. Krieger, AP Statistics. We're going to start AP exam review, and you're not going to like to hear this, but we're going to do a review of probability. Now I know I told you that you could kind of avoid the probability sections or the probability questions on the AP exam and still do very well, but now that they've turned the AP exam into a 45-minute test, I'm not sure that that strategy is going to work. So we're going to do some review of probability. Today we'll do the relatively simple probability, and then we'll probably do another lesson or two with more complex probability questions. Okay, so please make sure you have this lesson. Okay, an event is any outcome or a set of outcomes of a random phenomenon. For example, it is a subset of the sample space. Okay, example, rolling the sum of a 7 from the above dice example, how many outcomes can you have? But I wrote that out for you. Here is the sample space when you roll 2 dice. So there are 36 possibilities. To get it, so when you see all the possibilities, it's very easy to figure out a probability, because if we want to find the probability of getting a 7, we look for wherever the numbers add up to 7. So let's see. Right here, this adds up to 7, 4, 3, 5, 2, 6, 1. So it's actually this diagonal here. There are 6 cases out of 36, so it's a 1/6 chance of rolling a 7, okay? A probability model is a mathematical description of a random phenomenon consisting of 2 parts, a sample space and a way of assigning probabilities to events. Here are things you should already know. Any probability must be a number between 0 and 1. It can't be less than 0, it can't be greater than 1. 0 means it has no chance of happening. 1 means it's certain to happen. Okay? The sum of all probabilities in a sample space must equal 1. Like in our case with the with our rolling 2 dice, this is 7 out of a possible 36. But if you add up the probability of getting any combination, it's going to be 36 out of 36, which is 1. Okay. Addition rule. Now there are 2 addition rules for probabilities, and it depends on whether or not the events are mutually exclusive or not. So this is a situation where you have mutual exclusivity. Event A and event B cannot happen together. Sort of like when you, and I'll use this example later, when you pick a card from a deck of cards, you can't get a 2 and a king at the same time if you're choosing just one card. That's mutually exclusive. It's also called disjoint. And when you have mutually exclusive events, then you can find the probability of one of the other occurring is the sum of their individual probabilities. For example, the probability of event 1 is 45%, and the probability of event 2 is 25%. As long as these events are mutually exclusive, like A and B here, then the probability that either event 1 or event 2 occurs is the sum of those probabilities, okay? So this is the addition rule, and this is only for mutually exclusive events. Okay. Complement rule. The probability that an event does not occur is 1 minus the probability that the event does occur. We've seen this before. Sometimes it's indicated with a little c on top. AC is the complement of event A. The probability of the complement of event A is 1 minus the probability that A occurs. So this whole thing is the probability that A does not occur. Okay. Equally likely outcomes. If a random phenomena has k possible outcomes that are equally likely, then the probability of each individual outcome is 1 over k. For example, on a spinner, if you spin a spinner and all the sections are equally sized, let's say you have a spinner with 8 equally sized sections, the probability that any one section shows up is 1/8. Now here we see a new thing. We talked about mutually exclusive events, but we also have a thing, independent events. Now, independent events are events where one of the outcomes has no effect on the other thing's outcome, right? That's different from mutually exclusive. We'll take a look at that a little bit later as well, the difference between those 2 things, okay? If 2 events A and B are independent, in other words, the probability of one doesn't affect the outcome of one doesn't affect the outcome of the other, then that each of these events occur simultaneously, not I should say one after the other, is the probability of A times the probability of B. Okay, we'll take a look at examples like that later. Okay, let's try our first problem. And this problem has to do with mutually exclusive events. All these events are mutually exclusive. Let me tell you what we got here. People taking distance learning courses, the age group. Okay, from 18 to 23, the probability is 57%, 0.57, 24 to 29 is 17%, etc. Please notice that you can't be in this age category and simultaneously be in this age category. You can't be 17, let's say 19 and also 26. Those are mutually exclusive, so therefore we know the probabilities add. What's the probability that a person from this selected from this group at random is 30 years or older? That's going to be these two added together. Let me show you, yes. 0.14 plus 0.12 is 0.26. What's the probability that a person selected at random from this group is not 18 to 23 years? Well, that's going to be 1 minus the probability that they are 18 to 23. We know that's 0.57, so here we can see the complement rule, and that's going to be 0.43. And by the way, you can try these problems without my help. You could pause the video, but if you want to, I'm going to keep working, and you could try the problem before I get to them. Okay, blood types. All human blood can be typed as either OA, B, or AB. But distribution of types varies with race. Here is the distribution of blood types of a randomly chosen Black American. So this is specifically for Black Americans. Here we have the probability that a Black American has blood type O is 0.49, A 0.27, B 0.20. Let's try to find AB. Well, we know the sum of probabilities have to add up to 1. So we would need to add 0.49, 0.27, 0.20. Let's see what that gives us. So 49 and 27 is 76, 96. So this is 0.96. Then we would have to subtract that from 1. So this is going to be 0.04. Okay? Maria has type B blood. She can safely receive blood transfusions from people with blood types O and B. What is the probability that a randomly chosen Black American can donate blood to Maria? So we would have to add up the probability that they have O or the probability that they have B. Okay, and there is the probability that a randomly selected individual can donate blood to Maria. All right, now remember I told you the addition rule was adding the individual probabilities together, but that was for mutually exclusive events. Well, these events are not mutually exclusive. There's an overlap between A and B where they can occur at the same time. They can't occur at the same time in this wide section, but they can occur at the same time in this overlapping section, okay? So here's the rule if you have an overlap or things that are not mutually exclusive. If events A and B are not disjoint or mutually exclusive, they can occur simultaneously, and this is the probability of the union. It's add the probabilities of A and B, but subtract that overlap, A and B. That's this symbol, okay? So basically the reason why this works is because when you add the probability of A, it adds this whole circle, including that overlap. When you add B, you're adding this whole circle, but that overlap. So essentially you've added that section twice. So subtracting it off gets rid of one repetition of it. Okay, we'll try a problem. Here's a problem where you have to use a Venn diagram to solve it. Okay, Deborah and Matthew are anxiously awaiting word on whether they have been made partner at their law firm. Deborah guesses that her probability of making partner is 0.7 and that Matthew's is 0.5. If she also guesses that the probability that they both are made partners is 0.3, let's create a Venn diagram to illustrate this problem. So we know there's some overlap there. Here's the two circles. This will be for Deborah and this will be for Matthew. We always start with that overlap first. So there's a 30% chance that they both make partner, and then we're going to subtract that. For Deborah, it's 0.7, so her circle should be 0.7. 0.7 minus 0.3 is 0.4. For Matthew, it's 0.5. 0.5 minus 0.3 is 0.2. And also, we can put out the probability that neither of them makes partner, which would be out here. We add those together, that's 0.7, 0.9. 1 minus 0.9 is 0.1. There's a 10% chance that neither of them make partner. And now we can answer these questions. Okay, calculate these probabilities. You're welcome to do this on your own. I'll go through it. The probability that they are both promoted is 0.3. That was given. The probability that both of them are not promoted. Oh, I'm sorry. The probability that Deborah is promoted and Matthew is not promoted. That's this. Here, Deborah's promoted, but doesn't include the parts where Matthew is promoted, so it's 0.4. The probability that Deborah is not promoted and Matthew is promoted, that would be the opposite case here, 0.2. And the probability that Deborah is not promoted, that neither of them are promoted, basically we did that over here, that is 0.1. Okay, conditional probability. This is an important one. Okay. The probability we assign to an event can change if we know that some other event has occurred. Here's the notation. The probability that A occurs given B has occurred reads probability of A given B. A condition that has the same effect of reducing the size of the sample space and therefore the value of the denominator in the probability fraction. We're going to take a look at examples of that. Here's how we figure out conditional probability, or at least one way. The probability that B occurs, given that A has already occurred, is the probability that both things have occurred divided by the probability that A has occurred. That thing in the denominator. I'm sorry, the thing that has occurred already, that will be in the denominator. Okay, and here, this is just this rearranged. The probability that A and B occur simultaneously at the same time can be written as the probability that A occurs times the probability that B occurs given that A has already occurred. So we can actually see, and again, what I'm going to do is right here, I'll make the little and symbol. That's the and symbol here. We can turn this equation into this equation very simply. So you're welcome to use either of these equations depending on your circumstance, or you can just use one of the equations and just put in values that you know and cross multiply. But to show their equivalence, let me start with this. The probability that B, given that A has occurred, is the probability that A and B occurs over the probability of A. If we put this over 1, we can cross multiply. So P and A times 1 is the probability of P, the probability of A and B. And if we cross multiply these, we get that the probability of A times the probability of B given that A has occurred. Okay, so we'll try, here's one example that's done for you, and then we'll try a couple. 29% of internet users download music files, and 60% of the downloaders say they don't care if the music is copyrighted. So the percent of the internet users who download music event A and don't care about copyright event B is 60% of the 29% who download. So basically they're using this formula right here. So let's take a look. Probability, I'll write it this way, the probability of people who download music files is 0.67. I'm sorry, I made that mistake there. This is 0.29. And 60% of the downloaders say they don't care if the music is copyrighted. Okay? So the probability that they, hold on, I'm getting confused. You know what? Let's try to follow this example. Let's go on to the next thing. Let's take a look at this example. It's clear. Okay. If we have a contingency table, it works out really, really nicely. Contingency tables also help when calculating conditional probabilities. Here's a contingency table for grades awarded at a university by school. We have the grade A, B, below B, the total. We have the type of course taken, liberal arts, engineering, and physical sciences, health and human services, and these are the totals. So these are just totals, the marginal totals. So here we'll take a look, and it'll make the conditional probability a lot easier to see. What is the conditional probability that a grade at the university is an A, given that it comes from a liberal arts course? Well, let's use the formula they told us before. which is, I'll write it this way, the probability that you get an A and liberal arts divided by the probability of liberal arts. Probability of liberal arts. So this is the probability of getting an A given that it's from a liberal arts course. Okay? So let's do this that way. Using the definition, what's the probability of an A grade and a liberal arts course? Well, that's this section right here, 2142 over the total, 10,000. What's the probability of a randomly selected course being a liberal arts course? Well, that's 6,300 over 10,000. So now we can do the probability of both, which is this, 2142 over 10,000, divided by, I'm not going to have so much room here, the probability that's from a liberal arts course, which is 6,300 divided by 10,000. And this reduces to 2142 over 6,300. And here's a shortcut. If you know that the course taken was a liberal arts course, you can just simply look at this row right here. The probability that you're already in a liberal arts course and you get an A is 2142 out of 6,300, so you can get the solution right away that way. Okay, so let's take a look at this next problem. It's a little small, but hopefully you can read it on your paper. The probability that a new microwave oven will stop working in less than 2 years is 0.05. The probability that a new microwave oven is damaged during delivery and stops working in less than 2 years is 0.04. The probability that a new microwave oven is damaged during delivery is 0.1. Given that a new microwave oven is damaged during delivery, what's the probability that it stops working in less than 2 years? So let's write down a few things. First of all, the probability that it's not working in less than 2 years is 0.05. The probability that it's damaged and stops working, so it's damaged, I'll use D for damaged, and not working in less than 2 years, that's 0.04. The probability that the microwave oven is damaged during delivery is 0.10 or 0.1, and we want to find the probability that the microwave oven is not working in less than 2 years, given that it's damaged. We should know, and I'll put this on a separate sheet so you can see it clearly. I'll put it right over here. So we know that if we want this probability, we want the probability that it's damaged and not working in less than 2 years. Over the probability that it's damaged, and we can get that probability by putting this value over this value. So I'll put it over here. So this is equal to 0.04 over 0.10, which is 40%. Okay, so that's how you would solve a conditional probability question. And now we're going to take a look at independence. Okay, the conditional probability, the probability that B occurs given A has already occurred, is generally not equal to the unconditional probability, the probability that B occurs, because event A generally gives us some additional information about whether or not B occurs. If knowing A occurs gives us no additional information about B, then A and B are independent events. Here is the formal definition of independent events. If two events are independent, A and B, then the probability that B occurs, given that A has already occurred, will be the same as the probability that B occurs. Basically, A having occurred had no effect on B's outcome. It was independent of B, okay? Now we can take a quick look at how mutually exclusive events and independent events differ. Mutually exclusive events is usually one thing that you're doing. It is one thing you're doing. When picking a card, here's an example. When picking a card from a deck, a king and a 2 cannot be picked at the same time. You can't, on one selection of a card, get a king and a 2. Those are mutually exclusive. Here's independence. When picking a card from a deck, if the probability of picking a king is 4 out of 52, then it's independent of another pick. On the other hand, if a 2 has just been picked and not replaced, then the probability of selecting a king is now just 4 out of 51 because you took a card out of the deck, right? The 2 is on the side. You've essentially changed the size of the deck. So now the chance of picking a king is only 4 out of 51. Therefore, the two events, the first selection and the second selection, are not independent of each other. If we were to replace the card after, then we're making it independent. So if we replace the 2 and reshuffle the deck, then the probability of picking a king is again 4 out of 52. That would be independent. Okay, here's one last problem. Let's try a problem that involves the telling if something's independent. There's a 34% chance that a person picked at random from the adult population is a regular smoker of cigarettes, and there's an 18% chance that the person picked has emphysema. If the percent of the population that are both regular smokers and suffer from emphysema is 14%, so now the question is being a smoker independent of having emphysema? All right, so let's write down the key facts here. The probability of being a smoker is 0.34. The probability that a person picked at random suffers from emphysema is, regular smoker, 80% chance that they have emphysema, 0.18. Now it says the percent of the adult population that are both regular smokers and suffer from emphysema, so smoker and emphysema, is 0.14. It wants to know, is being a smoker independent of having emphysema? So let's take a look. We want to check to see if the probability of having emphysema and being a smoker, I just changed the order of that, but it's not any different, is equivalent to the probability of just having emphysema. If these are equal, then we know that the events are independent. Well, we know this already. This is 0.18. We know how to compute this. This is going to be, this is a mistake. The probability that a person has emphysema given that they're a smoker, this is a conditional probability, sorry about that. That we have to compute by doing the probability of E and S, the person has emphysema and is a smoker, over the probability that they're a smoker, because this in the denominator here is going to be whatever here. So this probability of the two things happening at the same time is 0.14. This probability we know is 0.34, and that equals 0.41. That is not equal to 0.18, so these events are not independent. Being a smoker has an effect on a person having emphysema. We all kind of know that smoking leads to emphysema a lot of the time. It's not the only cause of it, but being a smoker certainly increases the probability that you get emphysema. Okay, you now have the last 3 pages are homework. Please work on that, and until next time.